All right, so we throw around terms like big O all the time when we talk about algorithm complexity. But what are the actual official rules that make it all work? Today, we're diving into the formal properties of big O, big omega, and big theta. Think of this as the foundational grammar you need to analyze code with total confidence. So let's get into it. And you might be thinking, why on earth do I need to memorize a bunch of abstract math rules just to write code? And that's a totally fair question. But trust me, these properties aren't just for academics. They're the tools that let you take a gut feeling about an algorithm's speed and turn it into a cold, hard, verifiable fact. And here's the key that is going to make everything just click. For this whole explainer, let's use a really simple analogy. Think of big O as being less than or equal to, big omega is greater than or equal to, and big theta? Well, that's our equals sign. If you just keep this in your head, you're about to see how all these formal rules become incredibly intuitive. So here's our game plan. We'll start with the basic rules of order, sort of the bedrock of the whole system. Then we'll look at how these notations are all related. After that, we'll get into the algebra for simplifying complexity, and we'll wrap it all up with a super handy cheat sheet. Okay, first up, the basic rules of order. You can think of these as the properties that just confirm our notations behave in a logical, predictable way, just like the numbers we use every day. This is the foundation for everything else we're going to talk about. Let's start with something called the reflexive property. This one's super straightforward. It just says that any function is a bound of itself. So function, let's call it f of n, is always going to be big O of f of n, big omega of f of n, and big theta of f of n. For example, it shouldn't be a surprise that n squared is big O of n squared. It's a simple idea, but it's a really important starting point. And this is where our analogy just shines. This is exactly like saying any number is less than or equal to itself. I mean, of course it is. 5 is less than or equal to 5. Makes perfect sense, right? A function is its own boundary. Next up, we have the transitive property. This one is really useful because it lets us chain these relationships together. So if function f is bounded by g, and then g is bounded by h, well, it just logically follows that f has to be bounded by h too. And the cool thing is, this rule works for all three, big O, omega, and theta. Again, our analogy makes this crystal clear. If you know that a is less than or equal to b, and b is less than or equal to c, then you know for a fact that a has to be less than or equal to c. It's just a simple, logical chain reaction. Let's make this a little more real. Take a look at this table. We know that the function n is big O of n squared. We also know that n squared is big O of n cubed. Well, the transitive property lets us just connect those dots and say, with confidence, that n must therefore be big O of n cubed. See how that works? The highest bound in the whole chain becomes the final bound. All right, we've got the foundational rules down. Now let's look at the family connections. How do big O, omega, and theta actually play together? How do they relate to each other? This is where the whole system really starts to show its power. Now, this is a really important point. Symmetry only works for theta. If a function f is theta of g, then you can flip it right around and say that g is theta of f. It's a two-way street, but, and this is key, only when that bound is tight. And our analogy tells us exactly why. Remember, theta is like our equals sign. And if a equals b, then of course b equals a. It's completely obvious. But you can't do that with less than, right? If a is less than or equal to b, you can't just flip it and say b is less than or equal to a. And that's exactly why symmetry is a special property that only belongs to the tight bound of theta. But big O and big omega have their own fascinating relationship. It's called transpose symmetry. Here's how it works. If f of n is big O of g of n, you can flip it around and say that g of n must be big omega of f of n. They're like two sides of the very same coin. So, for instance, if n is O of n squared, that automatically means n squared has to be omega of n. And this right here, this is the golden rule. This is what ties it all together. If you can prove that some function, g of n, is both an upper bound, that's big O, and a lower bound, that's big omega, for your function f of n, then you have officially proven that it is a tight bound. It has to be theta. This is probably the moment where our analogy is the most powerful. Think about it. If I tell you that a number a is less than or equal to b, and a is also greater than or equal to b, well, there is only one possible conclusion in the entire universe.
A and B have to be the exact same number. And that's the exact same logic we're using for these notations.
All right, let's get practical. How do we actually use all these properties to clean up the messy complexity expressions that we get when we're analyzing real code? Welcome to the Algebra of Complexity. First things first, a super important rule for making things simpler: constant factors just don't matter. If your algorithm takes, say, 7n² steps, we just say its complexity is O of n². Why? Because as n gets really, really big, it's the n² part that's driving the growth, not that little constant 7. So we can just drop it.
Okay, so what if you have 2 blocks of code and they run one after the other, sequentially? Well, that's where we use the sum rule. You find the big O for each block, and the total complexity for the whole thing is just the big O of whichever one is bigger, the dominant one. So if you have an O of n loop and it's followed by an O of n² loop, the combined complexity is just O of n².
So here's the bottom line. When you're adding complexities, you find the heavyweight champion, the dominant term, and you can just ignore the rest. The faster growing function is always going to overshadow the slower one as n gets big enough. And what if you're multiplying, like a loop inside of another loop? Well, the rule is just as simple. You just multiply their bounds together. So if you have an O of n function nested inside an O of log n function, their product is simply O of n times log n.
Wow, we have covered a lot of ground. So let's pull everything we've learned together into one final, powerful cheat sheet that you can use anytime you need a quick refresher.
And here it is. You've got the core properties, reflexive and transitive, that give the system its structure. You've got the relationships, like transpose symmetry, that connect the different notations. And you have the algebraic rules, sum and product, that let us simplify real-world expressions. And right next to each one is that simple analogy that makes it all make sense. This is your toolkit. This is what you need to master complexity analysis. So now you have the official rulebook. The next time you're looking at a piece of code, or maybe even someone else's analysis, think about these properties. Are you correctly dropping the constants? Are you picking out the dominant term in a sum? Using these rules doesn't just get you the right answer, it gives you the power and the confidence to prove it. Happy coding!